benefit of having new members in the programming committee is that you also find new speakers. So one person in the program committee that is not here at the moment, but he is at the IHF meeting, is Willem Torgel. Willem is working for the for NLUUG Labs. Well, he found Roland, who will tell us everything about how quantum will solve everything.
Sort of. Can everybody hear me also in the back of the room? It's really, really echoey. It's really, really nasty. Okay. Yeah, so my name is Roland van Rijswijk-Deij. I'll do this in English because I noticed there are a few English speakers in the room. No, it's all right. It's all right. I can live with this. And indeed, I work for NLNet Labs. We are a small, not-for-profit organization that makes lots of great open-source software that many of you might be familiar with or even use. But I'm not going to talk about that because I want to talk to you about the quantum blockchain cloud. Because you can never have enough hypes in one sentence. I've been told it should be the smart quantum blockchain cloud with machine learning. But that didn't fit on the slide, so I kept it like this. Because I sort of want to take you through this whole buzz around quantum. Like Andreas, the previous speaker, talked about post-quantum cryptography, which is something that actually makes sense. And I want to help you make sense of all the other stuff. So there might be a few things that sound familiar, but I want to go into a little bit more detail than Andreas did. And I want to start with the hype word. That's the reason I actually wore a shirt. Because you can't talk about the Gartner hype cycle if you wear a t-shirt, so I put a shirt on this morning. And there is a lot of hype around quantum computing. Raise your hands who's familiar with the Gartner hype cycle? Right, look it up, because Gartner is generally hated by tech people because they talk to managers. But actually, this hype cycle thing is a really, really useful way to think about technology. So if you're not familiar with it, it has its own Wikipedia page. So look it up. So quantum, it's kind of hard to see, but quantum computing was here in 2018. It most surely is somewhere over here in 2019. Who has seen this in the news? Hands. Ooh, not that many people. Right, this is Google. Like Andreas, for those of you who weren't there, the last talk was about post-quantum crypto. Like Andreas said, there are a lot of big organizations who are investing in quantum computing because they want to get an edge. One of those organizations is Google, and they spent millions, if not billions of dollars on building quantum computers. And this is about them building a 53 qubit, and I'll tell you about qubits in a minute, quantum computer. As you can see, lots of people worked on this. This is from Nature. And what they said is, we have achieved quantum supremacy. Does anybody have any clue what quantum supremacy is? Okay, 2 people. Yeah, well, I'll get to that in a minute. What quantum supremacy is that you have built a quantum computer that can provably do something better than a classic computer could ever do. So they can solve the problem better than what a classic computer could do. And what they did was something to do with random numbers that I forgot the details about. When I read this, what I see is this. Quantum supremacy. So I even put an American-style date in there just to sort of make it a movie poster. And the problem with this is that the hype isn't helpful because it doesn't help you understand what you should really care about. And the amount of hyperbole that is used in the quantum world, I mean, they give blockchain people a run for their money. Google's quantum supremacy was very modestly compared to the Wright brothers' first flight. I personally take issue with that because it doesn't help you understand what they achieved. It just makes them look really cool. And that doesn't solve any problems. So how can we know what is true or not? How do we really understand what is happening? And is public key crypto, as we have it today, no longer safe, because that is the reason we're developing post-quantum crypto, which the last talk was about, is because quantum computers might someday break public key crypto. But now that Google has quantum supremacy, can we just pack up our shit and go because it's no longer safe? And that's actually what I want this talk to be about, to help you understand some of the challenges that are faced. And of course, I can talk to you about it, but the great people from HackerNoon say it's so much better. Quantum computing is at the end of the blockchain. I do hope so. Right? That would solve 2 problems in one go. Right, so I want to be a little bit, I'll try to make some more jokes, but I also want to give you some serious messages. Oh, sorry, that was too quick. And I want to talk about some facts, just to build a basic understanding, which is also what I have. I don't have more than a basic understanding of this, because this takes degrees in quantum physics to understand what a quantum computer actually does. And I have a degree in computer science, not in quantum physics. So I couldn't be on the Big Bang Theory. Quantum computers have something called qubits. This is something that you may have heard of before. And some of you may already be aware that the trick that a quantum computer can do is that a qubit can take on any number of states between 0 and 1 at the same time, and you can do computation on that. That is really the quantum computing for dummies, right? This is called superposition. The trick with qubits is also that you can entangle them, and that means that they somehow work together because their states are linked. I think Thomas, who is going to be talking after lunch, might be using that for some of his quantum crypto tricks. This leads to some really weird properties. Look up quantum teleportation, it just sounds so cool. We're living in science fiction. But this also plays a role in breaking classic public key cryptography. So to execute what is called the Shor algorithm, which Andreas talked about, but not everybody heard that, I'll repeat it quickly in a few slides, requires this property of a quantum computer to be able to execute it. So how do you build a qubit? The jury is actually out on that. There are lots of different approaches that people are trying. And what you can think of, in terms of that might be more familiar with you, is that you can store data on a hard drive, you can store it on a tape drive, or you can store it on a flash drive, but they're all slightly different technologies. And the same is true for building quantum computers and building qubits. There are different approaches, and though there seems to be some convergence on what designs work and what don't work, there are still lots of different designs out there. And most of those have really extreme requirements. They invariably require you to do stuff with superconductors, which means you need to make stuff really, really, really cold. That costs a lot of energy. So in that sense, it's very much like the blockchain. There's one that uses diamonds. There's one that uses powerful lasers. Look it up. There are some as a nerd, this really appeals to me because it's sci-fi. But again, it doesn't really help you to understand if this ever is going to be a reality that will help you solve new problems. And the holy grail is to keep qubits stable. And current records are that they keep them stable in the order of a minute. But in order to do meaningful computation, they need to be stable for much longer, and you want to keep those states stable. Right, then there is the problem of the physical versus the logical qubit. And this is where it gets murky quickly, because remember that Google quantum supremacy paper I showed you, they are talking about a 53 qubit machine. Are they talking about physical or logical qubits? So what is the difference? Well, it turns out that quantum computers by their nature are inherently noisy and unreliable. That means you may need lots and lots of physical qubits to create one logical qubit. So you combine sort of the power of lots and lots of physical qubits to create one logical qubit. That's the thing to take away from this. Also, to perform error-free computations, you need what is called quantum error correction, which is also an entire discipline of research, quantum error correction, right? So these are physicists, mathematicians, computer scientists. They all need to work together and they all need to make breakthroughs in their research. Also, as soon as the claims about qubits start flying, what are we talking about? Are we talking about logical qubits? Are we talking about physical qubits? Right? Because there are people that say, oh, you need hundreds or millions or billions of qubits to break public key cryptography. Which is it? Are those physical? Are those logical? And I'll show you some numbers in a minute. Okay, hands up, who heard about the company called DWave? Not that many people. Okay, DWave, if you follow the discussions about quantum computing and about the ability to break public key crypto, these guys invariably pop up in the discussion, and somebody in the thread on Slashdot or on Stack Exchange will say, haha, but DWave already has a 2048-bit qubit quantum computer, so what are we talking about? That quantum computer already exists. And actually they have a new model which they claim is coming out in mid-2020, which has 5,000 qubits. So are we done? Can we give up? The picture of the DWave 2000 device is actually from an article in Forbes, which is something that managers read. And that says, oh, quantum is really going to break crypto, misery, paranoia, and all of that. And then they show a picture of that. That thing cannot run Shor's algorithm and cannot break public key crypto. That is because it is not a general purpose quantum computer. It uses something called it's hard to pronounce, adiabatic quantum computing. And that does not mean it doesn't eat sugar. The jury is still out on whether this thing actually provides a speed up over classic computers. And now there's a team from Google that said, oh, we found an application for this thing where it outperforms a classic computer. But actually, people are still looking into whether actually that thing is worth its money. And it's applied to very specific problems in machine learning. But it's not what is called a general purpose computer. And I've been told, but now I'm really going to where I don't understand things, that this is, you can compare this to an analog quantum computer, and the general purpose one is a digital quantum computer on which you can execute algorithms. But the most important thing to take away is this thing cannot run Shor's algorithm, so this will not break your crypto. Good. So time for a quick summary. Making stable qubits and therefore making a good quantum computer is really hard. You need to solve problems in multiple disciplines: physics, mathematics, computer science. Engineering, thank you. Are you an engineer, sir? And qubits are highly unreliable. You need orders more physical qubits to create logical qubits. And the state of the art are machines with some 50-ish logical qubits with limited stability. Right, that's where we are today. Right, so you already saw a picture of Peter Shor where he was a little bit younger if you were here for the previous talk. This is the same guy, still doesn't have devil horns. Ask the other people that were already here if you don't get the joke. In 1994, he devised an algorithm that could help break public key crypto. I'm not going to explain how that was explained in a previous talk. You can look at the video if you missed that. The thing to take away is this was touted as a killer app for quantum computers. Before this guy came along, quantum computing was sort of a niche. People knew that they could that it in theory was possible, that it might be interesting, and then this guy came along and then people thought, hold on, that's interesting. If we can break public key crypto, ooh, if you're the NSA, that is interesting, or if you're the AIVD in the Netherlands. What his algorithm requires is a stable general purpose quantum computer to execute. Now let's assume that that exists for the sake of the argument. What are people doing with this algorithm? Because this algorithm has been around since 1994. Do you think scientists just sit on their hands? Of course they don't. So we don't just have people spending billions of dollars building quantum computers. We have people trying to improve the algorithm that you can run on a quantum computer that will break public key cryptography. They want to drive down the requirements to break common public key algorithms, and what I think is really awesome, that they can do this without the computer actually existing. So these people are so smart, they can reason about this without having the device to try their algorithm on. That's just fantastic. And this is from a very recent paper, a paper from this year. The thing to take away is the thing that I highlighted in yellow there. This is the number of physical qubits that the authors of this paper estimate you need in order to execute Shor's algorithm. The thing to take away is that yellow arrow gets smaller. That means the number of physical qubits goes down. That means we have a race to create more qubits with the people that are building the quantum computers, and we have a race to use fewer qubits with the people that want to break your crypto. Right. That might be a problem. What we also have is research to improve error correction. So they're not just trying to improve Shor's algorithm, but they're also trying to improve the error correction algorithms that allow you to use fewer physical qubits to create one logical qubit. One of the latest developments is called surface codes. So I don't know how we're going to share the slides, but I have lots of references at the end of the slides for people that want to dig deeper. Yes?
One question about the previous slide, the amount of qubits needed? Or those?
Yep.
Oh, sorry, those were physical.
Those were physical qubits, yes. Yeah. I will get to the logical ones in a minute. There was also an article, for those of you who are members of the ACM, there was an article in Communications of the ACM about surface codes last month, I think. Right, in the context of Shor, currently the surface codes give you, requires you to have approximately 15,000 physical qubits for one logical qubit, assuming an error rate of 10 to the power of -3. That is about the state of the art. Now, what is that error? As I told you, quantum computers are inherently noisy. This means is how many times when you measure a qubit do you get the wrong answer? And that's your error rate. And that sort of influences how much error correction you have to do. So the engineering needs to be improved. But then if you have better error correction code, the engineering can actually be sloppier. So all of these things need to go together, right? Again, another discipline that we need to add. Okay, so where does that get us with Shor's algorithm? This is a table that I took from a recent publication from the US National Academy of Sciences. Again, there is a link to all of the material I used at the end of the deck. I've highlighted two things. So the first is RSA, 2048-bit, which is, I guess, the most used variant of RSA at the moment. Gives you roughly 112 bits of security. You need in the order of 4,098 logical qubits to execute Shor's algorithm in about 28 hours to break one 2048-bit key. And that requires about 8.5 million physical qubits based on the latest insights. Elliptic curve crypto, 256 bits elliptic curve key gives you 128-bit security, 2,330 logical qubits, but roughly the same number of physical qubits required. Don't ask me why. Because that's a detail I don't understand. But it's interesting that for elliptic curve crypto, you actually need fewer logical qubits to solve that problem. It's easier to solve on a quantum computer, which is interesting because ECC is something that we tell people to move towards because it gives you smaller keys and better security with smaller keys. Now, I would still argue if you are using classic crypto, it doesn't really make that much of a difference whether you use RSA or ECC, and ECC has some really interesting properties. So I would still say use ECC, unlike the NSA. But then you only need 10.5 hours to break that key. But this is in the same order of magnitude, right? So it really doesn't matter which one of the two you're going for. Right. I'm going to talk about the little note at the bottom of the slide now. Terms and conditions apply. Hands up, how many people have I scared into thinking that your crypto will be broken soon in not a lot of time? You don't believe me? Okay. Right, that previous slide. That has a lot of assumptions about what a quantum computer can do, none of which hold today. Like literally none of them. Okay, so the $64 million question, of course, now is, when, if ever, will these assumptions hold? Anyway, that nobody knows. And this is a t-shirt I found. I can make this joke, that's fine. But somebody that gets quoted a lot is a guy called Michele Mosca, who runs a quantum computing institute. And his most recent prediction puts the likelihood of a quantum computer that can break 2048-bit RSA in the next decade, so the next 10 years, as a probability of 1 in 6. I have no clue where he gets that number. This is sort of following the developments in all of those fields that work on this, shaking a stick at it, reading some tea leaves, I don't know, reading some entrails of a bird, and then you say 1 in 6. That doesn't sound like a very, it sounds random to me, but this is something that a lot of people take seriously. Now, actually, it doesn't really matter if it's 1 in 6, if it's 1 in 1,000, if it's 1 in 100. This is about risk management, right? Okay, that's also what Andreas told you. It's about risk management. I'll get back to that in a minute. What do the experts actually agree on? Well, what they agree on is that nobody really knows if a quantum computer good enough to run Shor's algorithm will ever be built. They still don't know. Lots of people think it will happen, lots of people hope it will happen, and lots of taxpayer euros and dollars are being bet upon the fact that people can make this happen. But equally, nobody claims that it can never be built, right? So that's the opposite. Nobody says this cannot be done. That's something you should probably take seriously. But there is lots and lots of parallel research in multiple disciplines. I hope I convinced you of that. That needs to go through some major breakthroughs to get there. These are not trivial problems to solve. So what is the best thing that you can do if you want to make a decision today? Well, the thing that you can do is keep a keen eye on post-quantum crypto. For those of you who missed the last talk, the speaker gave an overview of what post-quantum crypto is and which algorithms they're working on. The takeaway from that is those algorithms also have their limitations. They still need to prove whether or not these are secure. They have performance issues. So this is also not a trivial problem to solve. But that's something you want to keep an eye on, because that's the one thing that you should be minding. You should be thinking about whether you need to transition to those sorts of technologies and whether the technology is mature enough to transition to one of these technologies. And this is again where Mr. Mosca comes in. There's something called Mosca's inequality, which is a very trivial equation. X plus y is greater than z. But it is sort of, you can think of this as a way of reasoning about whether you need to do something. So X is the amount of time you want to keep your data secret. In case of your credit card, that might be 3 years and then it expires. In case of the messages that you send over Signal, this might be a little bit longer. Like Andreas said in the previous talk, in case of your medical data, this might be a hell of a lot longer. Now, y is the amount of time it will take you to transition to post-quantum crypto. And those of you who are a little bit familiar with internet standards know that as soon as the IETF dreams up a new standard, that is, of course, instantly rolled out across the internet, right? This takes time. So when reasoning about this, you need to take that time into account as well. Now, you add those two numbers. If they are greater than z, which is the time we expect the time in which we expect people to build a quantum computer that can run Shor's algorithm and consequently break public key crypto, then you need to start worrying and you need to start investing in deploying PQC. If you're in the business of storing medical records, you may want to start thinking about that. If you're worrying about your credit card, who cares? It's not going to happen in the next 3 years. I think I dare say, I'll eat my shoe if it happens in the next 3 years. You can keep me to this. Oh, God. The thing is, the message I'm trying to get across is nobody really knows a sensible value for Z. That doesn't mean you shouldn't take action. But it also means you should take all of this hyperbole that is out there with a little bit of skepticism. But you might want to worry a little bit because the experts are on it. This is President Donald J. Trump signing the National Quantum Initiative into law, which is billion-dollar investment in getting an advantage in quantum computing. Now, you're laughing, right, because it's Donald Trump and he's so proud that he can sign something, right? I'm sure. Okay, and I mean, they have the other expert there as well. The reason you should actually take this seriously is that this was passed unanimously in the House. That means the Democrats and the Republicans agreed on something. Right? So everybody wants to get an in on quantum computing and they're spending tons of money on it. And while we're on the subject, we need some more hyperbole. This just sums up America in one picture, doesn't it? I mean, it has the jets, it has the flags and all of that. All right. I want to talk a little bit about something different, which Andreas briefly mentioned in the previous talk, but I want to go into it into a little bit more detail. And this is quantum key distribution. Who is not familiar with the concept of a one-time pad? Wow. Okay, a few people. Basically, a one-time pad is I take one letter and I replace it by another letter and I randomly do that. And each line on this one-time pad is for a single letter. You can only use it once. This is the only information theoretically secure cryptographic algorithm that we can prove. This is actually a real one-time pad that was developed by the NSA. That's a really cool read about the history of ciphers if you're interested. So, what quantum key distribution actually is a way to distribute a one-time pad from point A to point B. That's all it is. And the security of the thing relies on the fact that you can tell if the message was observed, and I'll get to that in a minute. A common implementation of this is to send polarized lights through a fiber optic cable, a technology I hope all of you are familiar with. So how does this work? So conceptually, it works like this. Of course, we have Alice and Bob, and I'm now a little bit sad that I have such poor Alice and Bob pictures after Andreas's beautiful Alice and Bob the Builder. Basically, what you do is you take light and you pick two polarization directions. Are you familiar with Polaroid sunglasses? Right? If you take the two glasses of the Polaroid sunglasses and you twist them and you hold them on top of each other, you can't look through it, you turn it, you can look through it. Polarization of light. It means you send it in one plane of direction. So you pick one polarization direction and you pick one that is like this, and then if the light is in this direction, it's a 1, and it's in the other direction, it's a 0. Or you take a twisted version where this is a 1 and this is 0. The trick is, in order to receive something that is either sent in one polarization base or in the other, you cannot know that in advance. You have to randomly pick one, and you randomly pick one to transmit. So what happens is, Alice transmits this message, 0, 1, 0, 0, etc. And for transmitting every bit, she randomly picks a polarization direction. So in this case, it's at an angle. In this case, it's at right angles. And she sends that to Bob. Now, Bob randomly needs to pick a direction in which he receives this message, and then he records whatever he receives. After they're done doing this, they tell each other, then Alice tells Bob which polarization direction she used, and of course Bob knows which ones he used to receive, and then he can compare, if they use the same direction to send and the same direction to receive, they actually correctly received the response. And in another case, they have to discard it, because if you picked the wrong direction to receive, you basically receive noise. You randomly receive a 0 or a 1. Okay, how does this help you distribute a one-time pad? Let's say we have Eve, who is trying to intercept that message. Now what Eve will do in order to be on this, to intercept that message is she will also have to randomly pick a basis in which she receives, and then she has to retransmit it to Bob. If she picks the wrong direction, and Bob actually picked the right one, she introduces errors into that message. So what you do at the end, because I used a toy example here with very short one-time pads, you pick a random part of the one-time pad that the other party received, and you compare notes. So Alice and Bob actually sacrifice part of their secret to compare notes. If that contains too many errors, Eve was in the middle. So this actually relies on that you can detect that there's an observer in the path. This is a very, very simple explanation. There's a lot more technology to this, but this sort of gets you to grasp the idea. Sounds elegant, right? There are some issues with this. The first issue with this is that you actually need classic cryptography to authenticate the communicating parties. Because how do I know I'm actually sending shit to Bob and not to Eve? So basically it's just a way to distribute a secret if you can vouch for the party that you're sending that secret to. More importantly though, it is vulnerable to attacks. There is the so-called photon splitting attack. Come on, that sounds awesome, people. And actually the thing is that quantum key distribution relies on a single photon being sent, single photon emission. That's physically not possible. So what they do is they approximate this. They try to send far less than a single photon, but because it's probabilistic, they might just send 2 photons and then you can take the other photon, observe it, and then you actually can have a chance to observe. You can use both polarization directions to observe, and you pick one of them. There's a Trojan attack, which is you just shine a very bright light into the channel, and this works on, Thomas, correct me if I'm wrong, this works on both ends of the channel, and what you can infer from the reflection of that light against the source is what the polarizer is doing on the other end. And this allows you to infer the polarization with 90% accuracy, the paper that I'm citing there. Now, of course, you can do all sorts of stuff to solve the... Yeah, you have a question.
What is less than a photon?
That's no photon. 0 point, I think the thing they use sends like 0.1 photon. Exactly. It's a very good question.
This question?
Yeah. So you can, basically these attacks get published. The people that make quantum key distribution devices, these are commercially available. The people that make these things try to solve those attacks and build a better quantum key distributor. But the question you should really be asking is, do I need that thing? Do we really need quantum key distributions? There's actually a good slide deck from people that work on these kinds of technologies where they say, this is a niche thing that you might have a very specific area of application where it makes sense, but in most cases, it's very expensive. You need 2 devices, of course, because you want to send and receive, and they're in the order of 25,000 euros to buy a single one. Imagine scaling this to your whole network, and you can multiply the costs. Oh, and you need dark fiber, of course, because you need to send this over a fiber optic cable that you own.
Does this have to be point-to-point, the fiber?
Yes, this has to be point-to-point, because as soon as you amplify this signal, you are an observer, right? This is another problem. In order to send this over longer distances, because the bit rate over about 50 kilometers is 1 megabit per second of transmitting a one-time pad. That already tells you that this is not suitable for many applications. If you want to send this over longer distances, you need a repeater. That is a point where you can intercept the one-time pad, so you build security problems into your system. Another issue. There are known attacks. How many are still to come? This is an arms race, and I'm not convinced that this can actually beat a FedEx truck full of one-time pads. Because, and this is actually an argument that is made by other people, and then the people that are interested in quantum key distribution say, yeah, but there are security issues with that because somebody could intercept a truck. Well, we understand those security problems really well, and we can do something about it. Right? We can put an armed guard on the truck or whatever if you're really serious about this. And one-time pads, physical one-time pads, have been the tool of choice for spies for a very long time. It's something that was used a lot in the Cold War because it's the only provably secure thing. People know how to deal with these physical one-time pads. Right, I want to start wrapping up. We have about 10 minutes left. So we can do some questions at the end. There is a lot of hype and hyperbole about quantum computing and it breaking public key cryptography. Just as there is about blockchain, that's why, of course, I wanted to sort of annoy people by saying blockchain. I hope I succeeded. There are two messages that I want you to take out of this talk. The first one is, don't panic. If somebody says they have quantum supremacy, throws billions of dollars at it, the fact that they're throwing billions of dollars at it right now means they haven't solved the problem. So don't panic. Don't start throwing away all of the crypto that you have, because it's still very usable. The other thing to do is pay attention to post-quantum crypto. Give people like Andreas, the previous speaker, who is a serious researcher who's working on this. There are some very talented people in the Netherlands that are working on post-quantum crypto. We actually have some of the best minds in this field here in this country. Give them money to do research. You need to give them far less money than the billions that people are chugging at building a quantum computer to get something that you can actually use. If I, as a taxpayer, I want money to go to these people. Unfortunately, quantum supremacy sounds so much cooler. But this is the work you should care about. With that, I'm at the end of my talk. I think we have some time left for questions. Fire away. Yeah.
You were talking about some breakthroughs needed to get to a computer running Shor's algorithm. But in the end, such a breakthrough will happen. How many breakthroughs are needed to get there?
Okay, so I'll repeat the question for the stream. The question is, I talked about breakthroughs in different fields that need to happen in order for us to get to a quantum computer that can execute Shor's algorithm. And the person that asked the question said, oh, but we're going to make those breakthroughs and we're going to get there. How many breakthroughs do we need? I think the jury is still even out on whether we are going to make those breakthroughs. Because one of the things is that as soon as you start, to take an example, as soon as you start adding qubits, if you start growing the number of qubits in your system, the instability increases. Right, so, and remember from the table I had there, you need in the order of 2,000 qubits to break something. We're at 50 now. It was really hard to get there. I have no idea how this scales, but it's probably not linear from 50 to 2,000. And whether or not we will ever be able to get there, whether or not we will, how much energy do we need to expend into that computer, we really don't know. So I couldn't tell you how many breakthroughs, but if I have to say what would be the hardest breakthroughs, those are the physics things to get there, to get systems that are stable, that have lots of qubits. Does that sort of answer your question? Yeah, it's a hard field. Other questions? Yeah.
So continuing that idea, so there is the theoretical quantum computer,
yep.
which is perfect, has a limited amount of qubits, like a Turing machine, say, but then for quantum. But what you're saying is that in practice, there are things that are hard if you have to build a real working one. Lots of qubits is hard, and runtime, long runtime is hard. These are the basic limitations of quantum computing. It sounds to me that we can get quite a bit more life out of our classical crypto by just making sure that it has to use a lot of qubits, for instance?
Yeah, so
What are your thoughts on that?
yeah, so the question is, getting a quantum computer to scale is really hard. Can't we just scale our crypto faster than people can build a quantum computer? Okay.
Just like we've done with
Just the classic crypto that we already have. So the answer to that is that will not work. Because what Shor's algorithm does is it makes solving the underlying hard problems in our current crypto really easy, regardless of it doesn't really scale very well with the number of bits. You could use like 32,000 bit RSA keys, and that means it would take a quantum computer longer to run Shor, but in the end it would get there. And that really scales very poorly. Your RSA becomes really computationally expensive to start competing with quantum computers. That doesn't work. That is why we were investing so much time and money in post-quantum crypto, where they're trying to replace the underlying hard problems in crypto by other hard problems that we think are remain hard to solve even if you have a quantum computer, right? That's the idea. The idea is that all of the problems we use right now are easy to solve on a quantum computer. With post-quantum crypto, we're trying to come up with new problems on which we build the new crypto systems. Does that answer your question?
No, not really. So
Okay.
say, you had that overview that said, say, for 2048 modulus RSA key.
Let me see if I can find that.
That
That one.
bits? Yeah, that one. So say, I need 4,000 logical qubits.
Yep.
So say if I have a quantum computer now which has 2,000 logical qubits, does it mean that it is useless?
Yes.
It cannot solve this.
Correct.
Until the point that I can actually build that thing, the 2048 bits RSA is fine.
Yes, it is.
So,
But as soon as you can build that thing, all of the stuff you encrypted with 2048 bit is useless. Yeah.
But this is, I mean, the amount of engineering that goes into that is not something.
Yes.
Oh, no, I have.
That was my message. So great.
Maybe as a follow-up, usually RSA is like the public key crypto is used for establishing something, right? And then you're switching to symmetric crypto, maybe with forward secrecy. How does quantum computing work in that regard?
Okay. So two things.
Or is this a whole separate?
To do key agreement, nowadays we typically use Diffie-Hellman because it's easier, but you can do it with RSA as well. And after that you use symmetric crypto. Now symmetric crypto is also affected by quantum computers. However, that's, you weren't here for the last talk, I guess. That's what is called Grover's algorithm. Now Grover's algorithm basically helps you do searches in random data. So basically brute forcing a symmetric key. And it reduces the search time from n to the square root of n. That means that you can very easily solve this by doubling your key size if you're using AES. If you're doing AES 128-bit now, just do AES 256-bit and you will be fine. And there is actually proof that you cannot do it better than that algorithm on a quantum computer. So symmetric crypto is absolutely fine. Asymmetric crypto is the thing to worry about. Yep?
Thanks.
Okay, good. One, I think last question? Yeah, okay. Yeah.
These figures, are these based upon mathematics, or is there some way to model a qubit?
That's a very good question. So the question is, are these based on mathematics, or is there a way to model a qubit? These are, this is an estimate based on where the researchers that wrote this think quantum computers are going. So they take multiple approaches to building qubits into account, they take multiple approaches to error correction into account, and then they say, okay, what is the most likely direction this is going to go in? And based on that, they make this estimate, right? It's all assumptions. But they are this is science, right? That sometimes you have to, if you don't know, you have to make assumptions. This is risk management. Are we ever going to get there? And I would say, so again, the link to the document is on the last slide. This is a very readable document that will tell you which assumptions they made and why those assumptions might be reasonable.
And the other part, modeling a qubit?
I don't know enough about that to answer that question. I wouldn't be able to tell you if it's possible or impossible.
Please go back to the last slide.
The last slide? Yeah, there we go. Oh, go ahead.
I want to thank you very much.
You're welcome.
Maybe my last question is, what does the quantum blockchain
Oh. I cancelled that slide. I can put it back in. Hold on. Unskip. So I think that this is the quantum blockchain. So it's a computer system in somebody else's data center you don't find out actually exists until you make a transaction that needs to be persisted on the ledger, after which it sets fire to the data center. That's the quantum blockchain.